So acids and bases are not like if you've seen Who Framed Roger Rabbit. Well, actually, not technically acids are in that, but in Who Framed Roger Rabbit, there's this scene where they take the cartoons and they're gonna like dip them in this vat of, I think it's actually like paint thinner, they call it toluene or something. But I think that's the sort of movie interpretation of acid, that if you dip something into it, it's going to completely dissolve everything except the bones, and when you pull it back out, you'll get a clean skeleton. It's not really how acids work. There are some acids that will do that, but not all acids. In fact, we eat acids a lot of the time. Things like citric acid, acetic acid, tartaric acid are found in a lot of different foods. Acetic acid, actually we've used several times this semester, is vinegar, albeit at a lower concentration in household vinegar. So when acids combine with saliva in your mouth, they actually produce protons, H+ ions. And you can taste those H+ ions because there are chemical receptors on your tongue. And when those chemical receptors pick up hydrogen, they send an electrical signal and you experience that as a sour taste. So you can taste protons. Anything that's sour, you're tasting those protons. So acids in general have a sour taste. They dissolve many metals. And they will turn blue litmus paper red. And litmus paper is just like, well, you use it to detect if something is acidic or basic. So if you have blue litmus paper, it's a test for acids and will turn red. We'll talk about bases later. So acids, used for a lot of different things. Like I said, the Hollywood movie version of acid, very different from the real world. So things like hydrochloric acid is used for metal cleaning or food preparation or refining. You've got a couple different fertilizers, sulfuric acid and nitric acid. Acetic acid is the active component in vinegar. And carbonic acid is found in carbonated beverages because the reaction between carbon dioxide and water. Carbonic acid is also in your blood. And helps regulate the CO2 levels in your body. It's how your body knows that you have too much CO2 and you need to breathe more. And then hydrofluoric acid is one of those super scary acids that will dissolve things that you put into it. Hydrofluoric acid will even dissolve glass. So you have to use special Teflon containers for hydrofluoric acid. There are a lot of chemicals to be afraid of. I am most afraid of hydrofluoric acid. So bases, in some ways, are the opposite of acids, and in talking about them, we're really going to talk about them sort of as the opposite of acids. Bases have a bitter taste, so you might expect maybe the opposite of sour to be sweet, but for bases, it's bitter taste. And we've actually, I think, talked about bases a little bit. Like bases are what make coffee bitter. So if you over-extract your coffee, you get too many bases out of it, and it's really bitter. Bases have a slippery feel, so like soaps. And then bases will turn red litmus paper blue. So blue litmus paper is used to detect acids, red litmus paper is used to detect bases, and they change color to the opposite color when they're detecting that. So just like acids, bases are used a lot in household products. There's some weird ones on here that I hadn't heard of, like Fantastic. But like Drano is, well, it's either sodium hydroxide or potassium hydroxide is the main ingredient because it will dissolve any hair that's in the drain.
They said that it's not good to use a lot of Drano.
Probably shouldn't be using a lot of Drano. If you have to use a lot of Drano, then you've got a different problem.
Well, I guess throughout years, because in the hospital, from using so much Drano, their pipes like broke and stuff when they were putting the snake in. Mm-hmm. And they said it's because of all the Drano from all these years using it.
That makes sense. Yeah, it's very corrosive. You also use, I don't think it's on this list actually, you can use bases, sodium hydroxide is lye. So concentrated sodium hydroxide is household lye, and you can get that for canning foods. So bases feel slippery because they're reacting with oils on your skin, and they form soap-like substances when they do that. And this is actually, the oils on your skin will protect you. So like if in the lab you do spill an acid or a base on your hand, it will start to react with those oils first before it gets to your skin, which protects you. So that's why you have a small window before you actually get a chemical burn. I did just a couple weeks ago accidentally pour 6 molar hydrochloric acid on my hand, and I rinsed it off and it was fine. So if you think you spill something on your hand, that's why you need to just rinse it off immediately, because if you do it immediately, then those oils will protect you. From most acids, from the acids and bases that we use. So bases are less common in foods than acids, partly because we don't like the way bitter things taste. And the reason is a lot of organic bases are found in plants that are toxic or poisonous. So the bitter taste is a warning against those poisons, which, even though that may be the case, people still drink black coffee. I actually had to train myself to drink black coffee because I didn't want to spend the time to put sugar in it. Acquired taste. Yeah, so sodium hydroxide, or if you've made soap at home, you also use sodium hydroxide to make soap. Potassium hydroxide, which some of these chemicals, at least sodium and potassium hydroxide, you probably are familiar at this point, seeing them in a lot of problems. But all kinds of different uses. Sodium bicarbonate is antacid, so like Tums. Neutralizes stomach acid. It can also be used as a source of CO2, so baking soda. All right, so the definition of acids that we're going to use, or well, one of the definitions, one of the first definitions is the Arrhenius definition. So by the Arrhenius definition, an acid produces H+ ions in aqueous solution. Let me switch to a different color, it's kind of dark. So it produces H+ ions in an aqueous solution. So if you add an acid, an Arrhenius acid, to water, it produces H+ ions, so hydrogens. So hydrochloric acid by itself does not contain any ions, but when you add it to water, the water ionizes it, breaks it apart into the hydrogens and the chlorides, which makes it a strong electrolyte, making it an Arrhenius acid. So those H+ ions are highly reactive, and that's what causes the acids to do things. It's not the whole compound itself, it's just those H+ ions. So they can react with water, right? So if we're adding our acid compound, hydrochloric acid, to water, then it reacts with the water to form something called hydronium. So this H3O+ is hydronium, and you will see a lot of the time, and I'll even write it this way, H+ written instead of H3O+, and those are just used interchangeably. But in reality, the H+ ion is always associated with water. They're never found alone. But it's just shorter to write H+, with the assumption that somebody reading your chemical equation is going to know that there's water associated with it. So when writing the molecular formula for an acid, usually write the ionizable hydrogen first. And this is something, I don't know if we really talked about it. The only acid I think that we've really used that has this, that does this, would be acetic acid. So So acetic acid, right? There's more than one hydrogen in the formula because that first hydrogen is the only ionizable hydrogen. The rest of the hydrogens don't leave when you add it to a solution. So for something like this is formic acid, we would write it with that H first, then a carbon, then a hydrogen, and then the oxygens. And then as a sort of skeletal structure here, see that ionizable hydrogen is attached to the oxygen, or one of the oxygens. All right, so bases, and we'll get to why they're the opposite of acids. Bases produce OH- ions in solution, in an aqueous solution. So if you add sodium hydroxide to water, it produces hydroxide ions, OH minus. And it's the fact that it produces those OH minus ions that makes it a base. So there are, right, so this NaOH, that will ionize, but there are molecular compounds that have OH groups, such as methanol, that do not dissociate in solution. As like a quick rule of thumb, the compounds that are going to dissociate are going to be ionic. So there's going to be a metal and then an OH. So here this is, right, sodium is a metal, and then that hydroxide is what ionizes. Organic compounds are things that are made with carbon. So this CH3 and the OH, right, there aren't any metals present. So that's not going to ionize into OH minus hydroxide ions. So under the Arrhenius definition of acids, or Arrhenius definition, acids and bases naturally combine to form water. And this is why they're opposites, because they neutralize each other. So if you have hydrogen, H+, and hydroxide, those can react to form a single water molecule, which is neutral. This doesn't explain, though, for all substances, that can act as bases. So some things, even though they don't add OH minus to a solution, end up creating hydroxides in the solution. So the Arrhenius definition is kind of an incomplete definition. So the better definition is the Bronsted-Lowry definition. And this kind of changes the perspective. So in the Arrhenius definition, we're looking at, okay, if we add this compound to water, does it create H+, does it add OH minus? And so it's like, what ion does it produce? It can produce one or the other. The Bronsted-Lowry definition changes the perspective to just look at where protons are going. So if something is accepting protons, then it's a base. If something donates protons, then it's an acid. So it doesn't contradict the Arrhenius definition, but it sort of expands on it. So something like HCl, when we add it to water, will become H plus Cl minus. And so it's still creating H plus, it's still adding H plus to the solution when it ionizes. And it's also donating this proton. So if we look at the periodic table, right, hydrogen, how many electrons does hydrogen have on the periodic table? 1. So if we take away that 1 electron, then it becomes H plus, and it becomes just a proton. So that's why we call hydrogen ions protons or H plus interchangeably. It's the same thing. So any H plus is actually a free proton flying around in the solution, which is what makes it so reactive. So this, should write this in here, proton. Proton gets donated, and then it can react with something else. So the proton gets donated to something else. And then if something accepts that proton, then it's a base. And so sodium hydroxide will create Na plus OH minus. And then this OH minus can react with NH plus to make water. So the OH minus is accepting the proton and becomes, and is a base because of that, because it accepts the proton. So the Bronsted-Lowry definition is all about exchanging protons. So this works for more things by focusing on the transfer of protons. So for example, HCl, like I just showed you, reacts with water, donates that proton to the water, which makes it an acid, a Bronsted-Lowry acid. So it's better accounting for what happens to that H plus ion from the solution, or from the acid. So really for acids, going from Arrhenius, Bronsted-Lowry, nothing really changes. For bases though, we can now include bases like ammonia. So ammonia is a base, but ammonia doesn't have any OH group in it. So it can't ionize to form OH minus by itself. But when ammonia reacts with water, it accepts a proton. All right, so one of these hydrogens gets transferred over to the ammonia, and then we get NH4 plus and an OH minus. So in this situation now, ammonia, becoming ammonium, is accepting one proton, accepting one hydrogen, making it a base, Bronsted-Lowry base. And so it makes the solution basic by increasing the concentration of OH minus in the solution. So there always has to be, and I know I wrote this earlier just to show you that like it still becomes a proton, still creates an OH minus, but there always has to be a proton donor and a proton acceptor. Kind of like, I don't know if this is a great analogy for how well you, depends on how well you remember redox reactions, but for redox reactions, it was all about an exchange of electrons. So the electrons have to go somewhere, and they have to come from somewhere. So there has to be a transfer from one compound to another. For acids and bases, it's the same thing. The acid has to be donating the proton to something. The proton can't just leave. And so in water, which are the only acids and bases we're going to talk about, that's usually the water itself. So the HCl donates one proton to the water, making it H3O plus. And then ammonia is a proton acceptor, and it's accepting that proton from the water again, and creating OH minus. And then there's a special definition. So here, water is acting as both an acid and a base. And water is a special type of compound, which is an amphoteric compound. So it can act as both an acid or a base. Now this is not, well, I think there's a better, I don't think there's a better one. Yeah, so water can act as both an acid or a base from the state of being just water. Right, so it's not like going back and forth, but from the same starting point, this can accept a proton, this can donate a proton. One of the other hallmarks of these acid-base reactions is that they are reversible. So NH3 was a base in this previous problem, right? NH3 is the base. But if we take that reaction and we reverse it, go the other way, now this NH4 plus is the acid, and the base is the OH minus. So when we're talking about what is the acid, what is the base, it's directional. So we're always talking about it in the forward direction, going from left to right, just like you would read a sentence. So if here the NH4 is, when written this way, is donating one proton to the OH minus, becomes water. And then the NH4 plus becomes the, okay, Netflix, YouTube, becomes ammonia. So it's now the NH4 plus is the acid, OH minus is the base. And then we call these conjugate acid-base pairs.
To the previous line, how did it, oh, okay, you just reverted it.
Mm-hmm. So we're literally just swapping the products and reactants. And actually, that's what this arrow here means. So that double arrow means that this reaction is happening in both, or can happen in both directions. Yeah.
Kind of like balancing them?
Kind of. Kind of.
So like the first one can't have an arrow going back the other way?
Yeah, and we're not going to get into that in this class. I don't know if you do that in Chem 1, but I know you definitely talk about a lot about that in Chem 2. Yeah. Right, so we can reverse those reactions. So then a conjugate acid-base pair is any two substances related to each other by the transfer of a proton. So like our NH3 and NH4 plus, those are a conjugate acid-base pair. So going in one direction, it's the acid. Going in the other direction, it's a base. So this is also a definition that you need to know. Do a better job highlighting that. Oh, that's nice. So yeah, one example would be so because these are related just by the transfer of one proton, they're always going to be present in a chemical reaction or chemical equation. So if you have ammonia acting as a base, on the opposite side you're going to have its conjugate base, or conjugate acid, I mean. And here water is acting as an acid, so on the other side it's the conjugate base. And when you're trying to identify what's the acid, what's the base, which one's the conjugate acid, which one's the conjugate base, acid and base are always reactants. Let's see, we're going to write this. Acid and base and then the conjugate acid and conjugate base are always products. So you're never going to have a conjugate acid or a conjugate base in the reactants, because it's the process of going from base to the conjugate acid. And together they're a conjugate acid-base pair. All right, so in each reaction, identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate base. So I'll zoom this in. So for this first one, for A, which one is the acid? Remember, acids donate protons. Yeah. So it's the acid here. Yeah, and so you can always tell if something is an acid because going from reactants to products, it will lose one hydrogen. And so we go from H2O to OH minus. And then I think that's pyridine, right? The C5H5N gains one proton. So it's accepting a proton, which makes it a base. And now what's going to be the conjugate acid? Yeah, the C5H5. So this is the conjugate acid. And then there's only one option left. It's the conjugate base. So acids, bases, always always reactants. Conjugate acid, conjugate base, always products. Not necessarily in this order every time, right? The acid could be the first one or the second one, compound in the reaction. So for B, which one is the acid? And sometimes you can use the fact of, well, depending on how familiar you are with the acids that we've been using in lab, or naming acids, right? HNO3 is nitric acid, unlikely to act as a base ever. So this is going to be an acid, which makes our base what? The water. So then our conjugate acid is water again. And then NO3 is going to be the conjugate base. So really, all you have to do is look for what is losing a proton, what's losing one hydrogen going from left to right, or what's gaining a hydrogen going from left to right. That's going to be, if it loses a proton, then it's a base, or sorry, if it loses a proton, then it's an acid. If it gains a proton, then it's a base. Yeah?
Because the definition is all about like the transfer of protons or OH minus. Is it the existence of the other pair, like the other thing in the pair that makes it acidic or basic? So like just a substance on its own, like hydrofluoric, like pure hydrofluoric acid, that wouldn't be acidic unless it has the base like with it, like water?
That's a great question. And yes, at least for this class, the definitions of acids and bases that we're using, that's correct. So if you have hydrofluoric acid, just pure acid, then that's not going to be acidic or basic by itself. It has to, under the Bronsted-Lowry definition, have something to donate a proton to. Yeah. And then if we take either of these reactions and reverse it, then we sort of swap the conjugate. And actually, just to show you what I mean, let me write that out. So NO3 minus plus H3O plus, 2NO3, H2O. So now, what's our acid?
Wait, loses proton is a base? Gains proton is an acid?
Opposite. So it's donating a proton, it's losing a proton, it's giving one away. Then that's the acid.
So losing is acid, gaining is base.
Yeah. So what's losing a proton?
The HNO3.
Well, we're going from left to right. Yeah. So this is the acid then. And then the NO3 minus would be the base. So then the conjugate acid would be the HNO3. And then the conjugate base is the H2O. So from our previous reaction, right, water here in B was the base. And when we reverse the reaction, now it's the conjugate base. Right, so that's what I meant when I said, when you reverse the reaction, the conjugate just stays on the product side. So NO3 minus is still a base. Or it's conjugate base here, but it stays a base, but now it's just the base, because it's accepting that proton. Okay. So acids and bases, if you have one of each in a solution, they will neutralize each other. So they will form water and a salt. We've talked about these types of reactions before, but didn't really talk about what acids or bases were. So we have our acid, hydrochloric acid, and potassium hydroxide as the base, and they form water and a salt. And so the net ionic equation for most neutralization reactions is going to be H plus OH minus makes water. Because when we add HCl or potassium hydroxide, so hydrochloric acid or potassium hydroxide to a solution, they ionize. They become H plus Cl minus plus K plus OH minus. All right, and then they become H2O plus so that would be a complete ionic reaction, or complete ionic equation, and then you cancel out all the stuff that stays the same. So the only thing left over is proton, hydroxide, and the water. So this is a neutralization reaction. And actually on Wednesday, we're going to use a neutralization reaction to do a titration and calculate the concentration of acetic acid actually in vinegar. So the reaction of acids with carbonates or bicarbonates produces water, and it also produces carbon dioxide and a salt. This was one of the gas evolution reactions that we talked about. You actually have sodium bicarbonate on the benches in the lab. So if you wanted to take a little bit of acid and a little bit of sodium bicarbonate and watch them fizz, you could do that. And that's this reaction that's happening. It's also a neutralization reaction. So we've got hydrochloric acid and sodium bicarbonate. And then that proton gets donated over here to the HCO3. It becomes H2CO3, which is unstable, and it breaks apart into water and carbon dioxide. So neutralization reactions, you can predict the products because the products are always going to be water and a salt. So if you have let's write a molecular equation for the reaction that occurs between H3PO4, so phosphoric acid, and sodium hydroxide. So H3PO4 plus NaOH. And the ionizable hydrogens are always written first. That also applies here. So phosphoric acid actually has 3 ionizable hydrogens. So there's 3 hydrogens that can ionize off in a solution. So what are the products going to be for this reaction? One of the products is always the same for a neutralization reaction. Water. So water is one of our products. And what would that leave behind? And we'll write the Na, so the metals are written first. So it'll be NaPO4. But what charge does phosphate have? -3. And that sodium's only a +1. So we need 3 sodiums.
Just balanced it, right?
It's not quite balanced. Not quite balanced yet. You can use, so hydrogen has a 1+ charge, so if you're adding, or if you're salt, so this would be our salt. I'll write this in, this is the salt. This is the water. If your metal or your cation for the salt has a 1+ charge, then you just need as many of the salt as you did hydrogens. So if here we have 3 hydrogens, then we need 3 sodiums. The 3 hydrogens also tells you that phosphate has a charge of 3- because it's got as many protons as it has negative charges to make it neutral. So then to balance this, here we have 3 hydrogens, and actually this is another trick. So OH already has 1 hydrogen. So when you're looking at how many hydrogens you need in the products, you're going to need, well, just know that half of them come from the OH-. So there's 3 from this. We need to add 3. Are
we supposed to balance it though?
Yeah. Sorry, I was just struggling. Because we need 3 sodiums. So then we could put a 3 here, and then that's 3 hydroxides. So then we'll get a total of 6 hydrogens. 3 of the hydrogens come from hydroxide, the other 3 come from phosphate. So if you start with balancing the other stuff, it will balance those as well.
When you do that, then you get 6 hydrogen on the right.
Yeah, so there's 6 hydrogens.
But over here on this side, there's only 4.
There's,
Oh, because the 3's there.
yeah, 3 there. So there's 3,
Right.
yeah. So this is called a polyprotic acid, so it's got more than 1 hydrogen. You'd have 1, 2, or 3 ionizable hydrogens. Not going to talk about this too much, but acids can dissolve many metals. These are redox reactions, so we've talked about redox reactions. And actually, you did a bunch of these reactions with that one experiment where you had the well plates and you had to like put all the stuff in and figure out the activity series. That's kind of like this. So I think copper was the only acid that you had, or the only metal that you had that didn't dissolve in acid. The zinc does, it just does so very, very slowly. So acids with metals react to produce hydrogen gas and then a salt. Some metals, like copper, don't react with acid. So, oh, we didn't do that one. There's a lab that we unfortunately had to skip. You generate hydrogen gas by dissolving a metal in acid, and at the end of the reaction, the metal is completely gone because acids react with metals in a way that causes them to dissolve into the solution. So it looks like they completely disappear, but they're really just dissolved, right? They're in the solution still.
It's in our schedule stuff, do we automatically get 50 points as we go to the left on that?
I mean,
You're gonna count towards, or you have it on there as counting towards the score, total score.
is it still on there? I thought I removed it.
No, I think
Well, I'll remove it, so
there was 12 points.
the rest of your labs will be out of 50 fewer points total.
I
So,
thought we did that lab already, where like that thing disappeared and then it reappeared again.
no, that was the molar mass of a volatile liquid. It's kind of similar. So acids can also react with metal oxides. And we're not going to spend a lot of time on these reactions, again, mostly focused on neutralization reactions. So the only difference here is that instead of producing hydrogen gas, if you're reacting an acid with a metal oxide, it produces water and a salt. So that salt will be made up of the metal from the metal oxide and then the anion from the acid. So we do just a couple examples of these. So reaction of hydrochloric acid with strontium metal. So HCl plus strontium. So if it's, where it's up here, acid plus metal, that'll give us H2 gas plus salt, and then an acid plus metal oxide will be H2O plus salt. So for this first reaction, what are the products going to be? Yep, hydrogen for one of them, because we have an acid and we have a metal. And a metal oxide means it's a metal with oxygen. So in this case, it's just strontium, so there's no oxygen present. So we'll get H2 plus Sr Cl2? Yeah. So when strontium becomes an ion, it's going to have a 2+ charge. And then to balance this, just add a 2. So for hydroiodic acid plus barium oxide, what are the products going to be? H2O. And what's the salt? Ba(I)2. So barium also, again, and you can use the periodic table for these. Right, so barium is in the second group, group 2, so it's going to have a 2+ charge when it's an ion. And then to balance this, just a 2 there. It won't always be 2 acid molecules to 1 metal or 1 metal oxide, just happened to be the case here. Okay. So the most important base reactions are neutralization reactions, which we did already talk about. And again, we're just going to kind of mention this before moving on. The only other kind of reaction that's covered in the book is sodium hydroxide with aluminum and water. So if you react sodium hydroxide with aluminum and water, you get this aluminum complex, which is soluble. So you can dissolve aluminum in strong base and water. So most metals don't dissolve when you add base. Aluminum is one of the few. Okay. So definitions, you need to know the difference between Arrhenius acid and Arrhenius base. So it's the first definition that we talked about. And then Bronsted-Lowry acid, Bronsted-Lowry base. Got to know the difference between those and what those are. And then the next most important thing is acid-base titrations. So solution stoichiometry, which we talked about before break, hopefully you remember that. Solution stoichiometry can be applied to a common laboratory procedure called a titration. So this is where you take a solution that has an unknown quantity of some acid or base, and you use an acid or a base, the opposite of whatever you're looking for. Use a solution with a known quantity of acid or base to figure out what the unknown quantity is. And we can do this because of stoichiometry. So the net ionic equation for any acid-base titration is going to be this H plus OH minus gives us H2O. And what we're trying to figure out is how much H plus do we need to add to neutralize however much OH minus is in the solution, or vice versa. Right? We'll know one of them, and we won't know the other, and we're trying to make all of it into water. So here we have an HCl solution represented by a molecular diagram. So we've just got hydrogens, because we don't really care about the chloride ions, we just care about the hydrogen ions. So only the H plus and OH minus are going to be shown. So here we've got what we can clearly see as 5 hydrogen ions. But obviously in the lab, right, you can't see the ions. So you're not going to know how many there are. So in this type of titration, we would add a solution of a known concentration of hydroxide, OH minus. So for you guys, that will be provided, and you'll know that it's exactly this concentration. And then as you add hydroxide to your unknown, those hydroxides are going to react with the hydrogens in the solution. Right, so for every hydroxide you add, it will neutralize 1 hydrogen until all of them are neutralized. And then we use something that's called an indicator, which tells us that we've reached the equivalence point. So it's called the equivalence point because the concentration of the acid is now equal to the concentration of the base, and it turns a very nice pink color.
You have to stir.
You do have to swirl it.
You do?
Mhm.
It won't just automatically like connect.
So yeah, this is something that you don't really think about a lot, but when you add two liquids together, they don't really mix until you stir them.
Not the bonds, the nitrons and the protons just like.
Well, you gotta remember they gotta move past each other to get to each other. So at the interface, right, where the two liquids meet, they'll be reacting there, but all of the liquid on top has to get to the liquid on the bottom to be able to react. And so when you swirl or mix, you're forcing those two things to meet. And that'll definitely be the case with this as well. So as you're adding in the titration solution, your sodium hydroxide, you'll see pink form in the middle. But as soon as you go to swirl it, it'll go back to clear. And then at some point you'll swirl it and it'll stay pink. And the challenge is to get the faintest pink color. And I'm a little bit red-green colorblind. So if you can get it so faintly pink that I can't tell that it's pink, then that's perfect. So the equivalence point, and actually let me write this out again. So we have H plus in our solution, don't know how much there is, and let me write it like this, like we have some unknown concentration, molarity of H plus, and then we're adding in some, I guess I'll write this, some known molarity of OH minus, and when, I should have written it as moles. Sorry, there should be some unknown number of moles of H plus, known number of moles OH minus. Because when the number of moles of H plus is equal to the number of moles of OH minus, that's the equivalence point. And it's important to hear that it's moles, because the concentration during the titration doesn't really matter. And actually, let me go back up to this as well. So for this acid-base titration, we're just going to call this, because there's 5 of those things, right? There's 5 hydrogens here. Let's just call this 5 molar H plus. And let's say that make it easy, there's 1 liter. Move this over. So if this is 5 molar, and we have 1 liter, then how many moles are there? There'd just be 5 moles, right? So 5 moles of H plus.
Are we assuming that's gas? That's not liquid, right? Nitrogen.
No, it's a liquid. Oh, so these are hydrogen ions, these are protons. It's not H2, it's just H plus. So it's in the solution. It is a liquid. So there's 5 moles of hydrogen in there. If I add more water to this, so let's say we can add another liter to this somehow. I know it doesn't look like it, but let's say that we add another liter of just pure water to this. Right, so now we have 5 moles. Well, actually, let me ask this question then. Does the number of moles of hydrogen change?
I'm confused. Because if it's water, it already has H2O.
H2O, sorry, okay. Let me rephrase it as protons. H plus. So we're talking specifically about the H plus from the HCl. So this is HCl.
There, but we're just not like talking about.
Yeah, we don't care about the hydrogens from the water. We only care about the hydrogens from the HCl. So these are just the protons from the HCl. So we've got 5 moles of protons. If I add more water, does it change the number of protons that are in the flask?
Yes.
Does it change the number of H plus from the HCl?
because you're adding more water, and the water has H.
But we don't care about water's protons.
Also, we're just talking about the Cl?
Yeah.
Okay, no,
The HCl protons.
I know.
Right. So the number of moles doesn't change, but if we increase this to 2 liters, so like if we take their 5 moles now, and we increase the volume to 2 liters, then the concentration changes. Right? It'll be 2.5 molar. But the number of protons stays the same. And the only thing that we care about, if we know the initial volume, so if we know we started with 10 milliliters, or 1 liter, we're going to add volume to this by adding the NaOH. The volume's going to increase, but the number of protons doesn't change. And so we're just trying to figure out how many protons there are in the solution. Definitely lost my train of thought. Okay, so and that's why this diagram here shows it the way it does, right? So the volume of this does increase, but there's 5 protons here. There's 3 protons by themselves here. The other 2 have been reacted with the hydroxide that's been added. And then here, we've got all of them have been reacted. Right? They've all reacted with hydroxide that's come from our known amount of hydroxide. So what we really want to know is, at the equivalence point, we know that the number of moles of hydrogen, H+, is equal to the moles of OH- that we've added. And so when our solution turns pink, we can use the amount of hydroxide added to calculate the amount of H+ that was present. We'll do some examples. So the equivalence point, it's usually an indicator. And an indicator is a dye whose color depends on the acidity of the solution. So usually the concentration of one of the reactants is unknown and the concentration of the other is precisely known. So for our reaction on Wednesday, you'll know the concentration of the sodium hydroxide exactly, or it might be potassium hydroxide. And you won't know the concentration of the vinegar that we're going to be testing. So for this to work, you need to know exactly how much of the acid, the volume of the acid, or the base, or the volume of the base that you've added. So we're going to use burettes, and those have really accurate markings for the volume added. Right, so if we know that, let's say we add 0.030 liters of sodium hydroxide, and the sodium hydroxide is 0.110 molar NaOH. Multiplying those together will tell us, maybe I should have picked easier numbers instead of more realistic numbers. All right, so this will tell us the number of moles of sodium hydroxide that's been added. So in this case, it would be 0.0033 moles of NaOH. And at the equivalence point, that would be the number of moles of H+ that was in the solution. Okay. So this is more of what it's going to look like. So we add sodium hydroxide to an HCl solution, very similar to what you're going to do on Wednesday. When the NaOH and HCl reach stoichiometric proportions, which just means that we have the same amount of each, then the indicator changes to pink. And then this is also kind of what it'll look like if you don't swirl it very well. You'll get pink in the middle, but it's also clear all around it. And so you need to mix it, swirl it, so that you're sure that all of the NaOH has had a chance to react that you've added.
It turns pink because it's an acid? Or
It turns pink when it's neutral. So when all of the acid and all of the base have reacted. And then the indicator is it's a special dye that you add to the solution. Yeah.
If it's like too pink, like not light enough, is that going to affect like our calculations or like how specific we are?
Yeah. So lighter pink is better because you're closer to the actual point where it starts to switch over. It does kind of go through a gradient. It'll go very quickly from a very light pink to a pink like this, and then it gets almost reddish if you get way too concentrated or way too much base. All right, so this is an example of the kind of problem you would get on an exam. So the titration of a 20 milliliter sample of sulfuric acid, H2SO4, of unknown concentration requires 22.87 milliliters of 0.158 molar potassium hydroxide solution to reach the equivalence point. What is the concentration in moles per liter or molarity of the unknown H2SO4 solution? So first you need to recognize that it's an acid-base titration, which in this case it tells you it's a titration, right? So you know it's a titration. You've got an acid, you've got a base. So you're going to need first a balanced chemical equation. So we're reacting H2SO4 and potassium hydroxide. What are our products going to be?
H2O for sure.
Water for sure. For sure.
And
Potassium's a metal, yeah. So potassium and SO4. Is the potassium though, is it one potassium, two potassiums, three? How many potassiums for every sulfate? How many hydrogens did sulfuric acid have? Two. So what does that mean that the charge on sulfate is? 2 minus. What's the charge of potassium? 1 plus. So we need 2 potassiums, yeah.
Why can't I do this test?
Test anxiety.
It is, it really is, like all that stuff on there.
Yeah.
I'm just gonna do this.
So to balance this, we need 2 potassiums. All right, so put a 2 for the KOH. And now we've got 2 oxygens. Put a 2 waters. And again, remember the SO4 oxygens, the O4, stays with the sulfate. So we don't need to balance that with the other oxygens. It'll balance itself as a group, SO4. All right, so that gives us a balanced chemical equation and also shows us something important about this reaction, that it's going to take 2 potassium hydroxides to neutralize every H2SO4. And now this basically becomes a stoichiometry problem. Because we have volume, we have molarity of potassium hydroxide, so we can calculate moles. And we want to know the concentration of H2SO4. So if it's 22.87 milliliters, we need to convert that into liters.
So what's the formula again? Moles equals, molarity equals moles over liters?
Yeah, molarity equals moles over liters. I was surprised I didn't see that one on the exam. So then milliliters to liters, so 1,000 milliliters is 1 liter. So that's going to be 0.02287 liters. And then our molarity is 0.158. So starting with, ooh, that's not it. So if we start with this 0.02287 liters of KOH solution, and then we use molarity, which is moles over liters, so 0.158 moles of KOH for every 1 liter of KOH. And we're trying to find, because we have the volume of the sulfuric acid solution, so we just need to find the number of moles of sulfuric acid.
So you would put 2 moles of KOH on the bottom
Mm-hmm.
and 1 mole of H2SO4 on top.
Yep, so it's a 1 to 2, 2 to 1 ratio.
And then put then a molar mass of H2SO4 on top and 1 mole of H2SO4.
So if we wanted to know the number of grams of H2SO4, then yes. But because it's asking for the concentration, and we have the number of milliliters, then we just need the number of moles. So this will give us moles of H2SO4. So in terms of the stoichiometry problem, we're done here. We don't have to go that extra step. So 0.02287 times 0.158 divided by 2. So this is going to equal 1.8067 times 10 to the negative 3 moles of H2SO4. And so the reason that we needed this balanced chemical equation was to get this mole ratio. Because it's not always 1 to 1. Yeah, not always 1 to 1. Okay, so then we can take that number of moles, so 1.8067 times 10 to the negative 3, and divide it by however many liters that we have of the solution, H2SO4 solution. So this is going to be 0.020 liters. So divided by 0.02. So the concentration of the solution is going to be 9.03 times 10 to the negative 2. Yep. Molar H2SO4. It's important for a titration problem to use the initial volume of your unknown solution. Because that's the one that's representative of whatever. Usually it's out of a batch, right? So you've got like a whole, let's say jug of sulfuric acid of some unknown concentration. So you pull out a small sample of that and you test that small sample. After you've done the titration, you've added more volume to it. You don't care about that extra volume because again, changing the volume doesn't change the number of moles of acid that's present. And actually on Wednesday, I'll even tell you if you have, well, you're going to use, I think you'll use 5 or 10 milliliters of acetic acid, and in a 250 ml Erlenmeyer flask, that's not very much liquid. You can add water to that so you have more volume. So it's a little easier to see the color.